Welcome to this first short recorded video on the Part B lecture notebook on numerical integration in the Module 4 Computational Applications. So in this first video, we will be discussing just the basic concepts of integration. We will also go over some basic code that shows how to use some numerical integration functions within Python, and also a class on integration that is useful within this lecture notebook. So what is an integral and why should we care? Well, the integral of a function can mean several things, and it depends a bit on the context, which also explains why we care about an integral. Typically, it refers to transforming a function into a scalar quantity, meaning a number. It could be a complex number, but for our purposes, it's a real valued number. And this describes some type of important aggregate behavior of the function over a set. An integration of a function is kind of like summing up the behavior of a function over a set in order to make important inferences. So some important examples of what this means are given below. In probability theory, the functions that quantify scalar outputs of an experiment are called random variables. And when you integrate a random variable weighted by the probability density function, you'll get the expected value of the experiment. Other standard statistical quantities such as variance also involve integrals. In engineering, design, and manufacturing processes, it is often important to compute the length of a curve, the area of a region, the volume of an object, surface area. And this helps you to determine the amount of resources or cost in constructing an object. This is also related to the homework assignment. Such quantities are given by integrals. In physics, integrals are used to determine important quantities like velocity, which is an integration of acceleration, and displacement, which is an integral of velocity. In finance, integrations are often used to determine things like options pricing, and many models of complex physical phenomenon involve partial differential equations, often referred to as PDEs, and these are often solved via numerical methods that often require computations of many integrals to construct accurate approximations. And then finally, in data science and statistical and machine learning and any other data-driven discipline where proposed models are fitted to data, the so-called goodness of fit of a model can usually be described in terms of an integral, or its discrete counterpart, summation. So that gives a lot of motivation about why we care about integrals and what they could mean in different contexts. But what is an integral actually, mathematically speaking? Well, to answer that, we first look at some notation. There are a few different notational conventions, but here we use the following. If f is a function, we let a denote some subset of the domain of the function. So it defines some acceptable set of inputs for the domain of the function. And then the integral of f over a is denoted by this notation where it looks like an elongated s. You can think of that as like an infinite summation with that elongated s. You use a usually as a subscript to denote the domain of the integration, and then you'll have f of x. Sometimes you'll see some other like dx or other notation here. Depending on the class you're in, the instructor might consider that optional. Here we'll consider it optional. This just really means the integral of the function f of x in kind of a base form here. A standard motivating example so that we can understand what an integral means is involving the integral of velocity to get displacement. And you'll see that this makes sense because of units. So we are going to avoid any complicating calculus details, but we're going to build intuition. So in this case, the general details for this motivating example are: suppose that v of t describes the velocity of an object moving either forward or backward on some path over the time interval t naught, t sub 0 is also called t naught, and t sub f, which is the final time. So t naught is the initial time. Suppose we are interested in how far along the path the object ultimately ends up relative to its starting position. This would be given by the integral over the set of times, t naught to tf, that interval of times, v of t. So some examples that have intuitive solutions are given below. For simple functions of v of t, we can easily conceptualize the problem and really use our intuition to figure out what the solution is with very little difficulty. So again, meaning little difficulty means no calculus. So consider the following scenarios. V of t is equal to 0. The object is not moving. Well, then the integral of v of t is 0, which means the final displacement of the object from its initial position is 0 units of length. Again, this is not surprising. The object did not move. Suppose instead, though, that over half the interval from t naught to tf plus t naught over 2, so that's half the time, It's moving with a positive direction, and in a certain direction that we denote as the positive direction, with a speed of 5, ignoring whatever the units are. It could be meters per second, miles per hour, it doesn't matter. And then it has that same speed, but it moves in the opposite direction, so it has -5 over the last half. Well, in this case, it's moving forward half the time at a constant speed, and at the other half of the time, it's moving backwards at that same speed. Again, the integral of v of t is 0 because the object just did a simple round trip to end up back where it started. So suppose, though, that now we have the same velocity as the previous example, but instead we wanted to know the total distance traveled instead of just the final displacement from the starting position. So in this case, we're interested more in the speed, which is given by the absolute value of the velocity, and we want to know the integral of the absolute value of v. So this is now giving us the total distance. So if you think of it as driving like a car, if you drove a car at a constant speed out of, let's say, a garage or some parking spot, and then you just turned around and came back at the same speed, and you did that over the same period of time, you'd end up in the same parking spot. But that doesn't mean that you didn't travel a distance. And if you wanted to know the distance you traveled, you need to integrate the absolute value of v. So what is the integral of the absolute value of v? Well, if you look at this, you'd say, okay, let's use some units now. Suppose v of t is described in miles per hour in terms of the units. Then what you really want to know is how many hours did I travel given the constant miles per hour. We're assuming a constant speed here of 5, let's say 5 miles per hour. Then if you took miles divided by hour, which is the units of the speed, and you multiply by the length of time in hours, the hours you could see kind of cancel out, and you're left with the miles traveled. This would be what shows up on your odometer in terms of the amount of distance you traveled. So in this case, you can see, oh, this is given by 5 times, because that's the absolute value of v is 5, t of f minus t naught, which is the length of time in hours. If 5 was given in miles per hour, the amount of time you traveled is tf minus t naught, assuming those units are given in hours. And you just multiply these two numbers together, 5 and this length of this interval. So to visualize these results, because we're going to build up to understanding what an integral means in terms of its relationship to a curve, we're going to define a function v of t. We're going to look at t given as an array of times. Tf is, we're going to assume t0 is given as 0, and tf is some final time. And then we're going to look at the times that are less than half the final time and make those equal to 5 for the velocity and -5 for the other half. And then we're just going to return these velocities, these v's. So I define this very simple function. And then here what I'm doing is just plotting. I'm going to look at 0 to 10 as my length of time. I'm going to create this linspace here. I'm not using the, this n equals this number of points. Here, I'm not putting a number of points for this linspace, so it's just using its default value. I am now going to do plotting. And on this plot, I am going to plot the function of velocity, and I'm also going to shade the region associated with the integral. So you can see what I'm doing here carefully. You can pause this video and read through. I'm just creating some vertices and a polygon that I then add as a patch that has some face color of 0.9. It's going to be gray. And the whole point of this is just to shade in a region between the curve and the axes. So here is our velocity, or the absolute value of the velocity. So I'm plotting, I said I was plotting velocity. I'm plotting the absolute value of the velocity. And you can see it's this constant 5. And then this area of this rectangle that's given by the shaded region, that's the polygon, is given by 5 times this length tf minus t naught. So we see, oh, that displacement that we had, the total distance we traveled, the integral of the absolute value of v, is just given by the area of this rectangle. And that area of the rectangle has a height of 5 and a length of tf minus t naught. And in this case, I chose t naught to be 0. Now, if I plot just the velocity, and I do the same thing where I shade between the curve and the axes, then you'll notice that these two rectangles, one above the x-axis and one below the x-axis, and the area of those two rectangles are the same. But the integral of v in this case we knew to be 0 because it was 5 and then -5. This was the total amount of displacement from the initial starting position. So in this case, we see if we integrate a function that changes signs, it appears that the area that is shaded between the curve and the x-axis when the curve is positive is canceled out by any area that's below the x-axis. So we might consider the area underneath the x-axis as being negative. And this explains what the integral, in a sense, is. These integrals are related to the areas of the shaded rectangles. And in particular, the integral of the absolute value is exactly the area of the single shaded rectangle. On the other hand, the integral of v of t is given by the area of the rectangle above the t-axis. I think I said x-axis, I'm sorry, t-axis because it's time, minus the area of the rectangle below the t-axis. They appear to cancel each other out. So we think of the areas as being signed, so that any area above a horizontal axis is positive and any area below the horizontal axis is negative. So the integral in general of a function is actually the sum of the signed areas. These observations lead us to the useful conceptualization of integrals in terms of sizes of positive and negative regions of a function over a set. So below, what I'm doing is I visualize the sign of an integral for a function in terms of what dominates, the positive or negative areas. And I use the quad function to compute accurate approximations of the integral. Now, we were exposed to this quad function actually in the activity to the prologue lecture, the external activity. It was used in the Fourier series approximations that were created to compute the coefficients. So the quad function is within the integrate subpackage of SciPy. I suggest taking 5 to 10 minutes to review some of the documentation you can find at this link. The quad function returns a tuple as an output. Much like our compute bisection function from the Part A lecture notebook, the first component in this is the approximation of the integral. The second component is an approximation of the error in the integral. Therefore, we usually append a 0 to the end of the call of this function so that we just return the accurate approximation of the integral. So you'll note this below. I'll just point out in the code where I use quad, here we go, it's right here. I append that 0 so that I only return the first output of quad into this approximate integral over the interval a to b. That's what that variable notation means. If you peruse the source code for the quad function, you'll also notice some nice docstrings, doctests, etc. that show good coding practices. So again, I provide a link here for you to look at it. It's on GitHub. The integrate subpackage is itself rather interesting and useful to familiarize yourself with, especially if you're going to do some computational data science applications or just general work in that field or you're interested. So I highly recommend looking at this tutorial that I reference here. For now, though, let's just import the quad function from scipy.integrate. And then this plot integral, it has this similar flavor than what we saw in the Part A lecture notebook in that all the computations are done here. I get my approximation of the integral. So I'm passing a function f, some min and max x values that are used for plotting, the interval a to b, like a left and right endpoint a to b that I'm integrating over, and a figure number just to control what figure numbers I'm plotting. I get the estimate for the integral right here, and then everything else below is plotting. And the whole point of everything else below is to, one, plot the function itself. So that's one thing that will get plotted. So I create the x values. I do 101 points. You might make that a parameter, that number of points, and then make that like an n that's passed. If you want, that's not a bad idea. I'm taking y equals f of x, and you'll notice I'm plotting the curve here. So I look at a figure that's given a certain figure number. If it had anything already in that figure number, I clear the figure, and then I plot the curve. And I plot it as a red line with a thick line width of 2. Then I plot a typical x-axis, or you could just call it a horizontal axis. And then everything else is making that shaded region by creating a polygon based on evaluating the curve at a set of points and shading it in as a patch. That's all that this is doing down here. And then I'm just setting up some stuff involving how I'm making the plot look down below. So it looks like a lot of code. It looks like 33 lines, even with some spacing. But in the end, all the computations here and everything else is about the visual storytelling of how to interpret the integral. So we'll go ahead and run that. And now I'm going to show you this way to interact with this plot integral function. That was the name of this, plot integral. And when I run it, I'm looking at integrating a function. Here it's x plus 1 times x minus 5 times sine of 3x. I'm going to plot it from -1 to 5, and then I'm going to set a and b values with sliders to look at the integral. So when I run this and I look at it, here's that curve, and it has some interesting oscillatory behavior. It's both positive and negative. And when you look at it, the whole point of this again is to drive home the concept of the sign of the integral in terms of what dominates, the positive or negative area. And you could see that the area below the x-axis, so let's call that the negative area again, seems to be much larger than the positive area. And the integral value, which I'm putting in the title, seems to be negative, negative 1.72. Now you could see if I move the a value, let's say more to, let's say over to that region right here, so it's at 2, so maybe move it over to like, let's say 2.7. Now the area is positive because there's more of this positive area compared to this negative area. Whereas if I move this b value down, let's say down to 3.2, now again I have more negative area than positive area, and the integral value again appears to be negative. So you can play around with this. You can also see what's interesting to happen. What happens if you switch a and b? It appears that there's more negative area than positive area, yet the value is positive. Well, the b value is now less than a, and I'm integrating from a to b. So if I'm moving in some sense, like it's like moving backwards in time, but I started in a, it kind of changes the sign of things. It treats what's below the axis as positive and what's above as negative if you make b less than a. So that's an interesting thing to observe in terms of integration. It's something that is explored in a calculus class. But you can just play with this a little bit, and you can see there's very nice plotting, and you can see it doesn't take much code to create kind of a nice widget that explores integration concepts in Python. So then the final thing I want to talk about in this video is just creating an integration class. So this is a suggested activity for you. You should add some doc strings to this class and add some code comments. But in this integration class, I want to just put some of the functionality we've talked about so far. I want to create objects based on an initialization of a function so I can just explore integrals involving that function. And this is assumed to be a function of a real valued function that's defined on the real line, or at least on some interval of values that you would restrict the evaluation of the object to. So you initialize it with a function f that you can evaluate. It could be a lambda function or some function you define. And I'm going to assume that a and b don't have to be given at initialization because you might want to specify them later. And then you initialize this function. So again, you should input maybe doc strings in here. Then you could set the integral limits. So you could set the a and b. That's a method that we have within that class. Then when we look at evaluating the integral, you would have to give a and b values. If they were already none, then you would have to say, okay, if a is not none and b is not none, when you evaluate the integral, if you hadn't already set a and b at some point, you would need to set it here. Otherwise, you would get an error when you run this. I'm not checking to see if self.a and self.b are ever none. But if you pass an a or a b to it, it will overwrite whatever a and b was previously. And then it will evaluate the integral. What I've done below then with this next method is plot the integration. So for that function that you use to instantiate this class, you can then explore the integral with and create plots of things that describe visually what's going on with the integration. You should set x min and x max values for the plotting. If you don't, we'll just use the a and b values that are given. And you can also change the number of points that you're plotting, like I suggested you do in the plot function. And again, you can control the fig num. And then again, all I'm doing, I create an array of x values, the array of y values that are associated with evaluating the function. I plot the function. I plot a typical axis. I create the shaded region. And then I just do the rest of the plotting, set the title and so forth. And then, excuse me, then I have the method to evaluate and plot the integral. So here you actually evaluate the integral with a given a and b value, and then you plot the result with that method. So just so you can see how it works, imagine I have that function x plus 1 times x minus 5 times sine of 3x. It's a lambda function. I passed it to integration. So this creates that object f integral. And now I can just interact with f.integral, evaluate and plot integral, and just like I did before. So again, if I run interact, this is going to look just like what we've seen before. But one thing I suggest you do, other than make improve the documentation on here, actually add documentation and code comments, is play around with this a little bit. Create your own different instantiations of the class with different functions, and look at some interactive widget interactions with the plotting and non-widget interactions with the plotting, and just get some intuition about integration if you're new to the idea of it. Now there is some context here. and context is everything. These are just one-dimensional examples. So above, I've just looked at functions with univariate inputs, meaning like a single number. Subsequently, we observe that the integral is related to the signed area between the curve defined by the function and the axis defined by the input. Now, of course, this observation can be conceptually extended to functions with multivariate inputs. So imagine a function with two inputs. So then your input region, instead of being like an interval on the real line that you're integrating over, you might be integrating over a set in a plane. In that case, the integral is related to the volume between the surface of the graph and the region in the plane instead of just area. And you can generalize concepts of area and volumes to even higher dimensional spaces, but we're going to stick with one-dimensional examples for the most part to explore the typical numerical algorithms. I will show a little bit about integration over a 2D space at the very bottom of this notebook. But that's it for now. Thanks for listening. The next video will actually start describing what we're doing with numerical integration and rectangle rules in this notebook.